Welcome to Flourish. I'm Diane, and you're in the right place if you're ready to create an inspired life. And we do so by working on our own personal development, so we can be strong role models for those we love and mentor. Today is week 1, chapter 5, in my journey through Psych-100 at Queen's University, Statistical Thinking. So let's get started. As our society increasingly calls for evidence-based decision-making, it is important to consider how and when we can draw valid inferences from data. This module will use 4 recent research studies to highlight key elements of statistical investigation. We begin with the learning objectives to keep in the back of your mind. I am not a teacher, I am a student, and it just helps me to think about these things as I study the information. So 1, define basic elements of a statistical investigation. Describe the role of p-values and confidence intervals in statistical inference. That's my dog Odie, if you hear a jingle. Describe the role of random sampling in generalizing conclusions from a sample to a population. Describe the role of random assignment in drawing cause and effect conclusions. And finally, critique statistical studies. Introduction. Does drinking coffee actually increase your life expectancy? A recent study found that men who drank at least 6 cups of coffee a day had a 10% lower chance of dying. Women, 15% lower than those who drank none. Does this mean you should pick up or increase your own coffee habit? Modern society has become awash in studies such as this. You can read about several such studies in the news every day. Moreover, data abound everywhere in modern life. Conducting such a study well and interpreting the results of such studies well for making informed decisions or setting policies requires understanding basic ideas of statistics, the science of gaining insight from data. Rather than relying on anecdote and intuition, statistics allows us to systematically study phenomena of interest. Key components to a statistical investigation are planning the study. Start by asking a testable research question and deciding how to collect data. For example, how long was the study period of the coffee study? How many people were recruited for the study? How were they recruited and from where? How old were they? What other variables were recorded about the individuals, such as smoking habits, on the comprehensive lifestyle questionnaires? Were changes made to the participants' coffee habits during the course of the study? Next is examining the data. What are the appropriate ways to examine the data? What graphs are relevant and what do they reveal? What descriptive statistics can be calculated to summarize relevant aspects of the data and what do they reveal? What patterns do you see in the data? Are there any individual observations that deviate from the overall pattern and what do they reveal? For example, in the coffee study, did the proportions differ when we compared the smokers to the non-smokers? Is there evidence for reliability and validity? Inferring from the data. What are the valid statistical methods for drawing inferences beyond the data you collected? In the coffee study, is the 15% reduction in risk of death something that could have happened just by chance? And then finally, drawing conclusions. Based on what you learned from your data, what conclusions can you draw? Who do you think these conclusions apply to? Were the people in the coffee study older, healthy, living in cities? Can you draw a cause and effect conclusion about your treatments? Are scientists now saying that coffee drinking is the cause of decreased risk of death? Notice that the numerical analysis, crunching numbers on the computer, comprises only a small part of overall statistical investigation. In this module, you will see how we can answer some of these questions and what questions you should be asking about any statistical investigation you read about. Next is distributional thinking. When data are collected to address a particular question, an important first step is to think of meaningful ways to organize and examine the data. The most fundamental principle of statistics is that data vary. The pattern of that variation is crucial to capture and to understand. Often, careful presentation of the data will address many of the research questions without requiring more sophisticated analysis. It may, however, point to additional questions that need to be examined in more detail. Example 1. Researchers investigated whether cancer pamphlets are written at an appropriate level to be read and understood by cancer patients. Tests of reading ability were given to 63 patients. In addition, readability level was determined for a sample of 30 pamphlets based on characteristics such as the length of the words and sentences in the pamphlet. The results, reported in terms of grade level, are displayed in Table 1. Now, if you're listening to this on the podcast, they have the patients' reading levels and the count of the number of patients, and then the pamphlet reading levels and the count of number of pamphlets. So the frequency table of patients' reading levels and pamphlet readability levels is what we're looking at. So these two variables reveal two fundamental aspects of statistical thinking. Data vary. More specifically, values of a variable, such as reading level of a cancer patient or readability level of a cancer pamphlet, vary. Analyzing the pattern of variation, called the distribution of the variable, often reveals insights. Addressing the research question of whether the cancer pamphlets are written at appropriate levels for the cancer patients requires comparing the two distributions. A naive comparison might focus only on the centers of the distributions. Both medians turn out to be ninth grade, but considering only medians ignores the variability in the overall distribution of these data. A more illuminating approach is to compare the entire distributions, for example, with a graph as in Figure 1. So they have another figure here, if you're watching this, in the comparison of patient reading levels and pamphlet readability levels. So in Figure 1, makes clear that the two distributions are not well aligned at all. The most glaring discrepancy is that many patients, 17 out of 63, or 27% to be precise, have a reading level below that of most readable pamphlet. These patients will need help to understand the information provided in the cancer pamphlets. Notice that this conclusion follows from considering the distributions as a whole, not simply measures of a center of variability, and that the graph contrasts those distributions more immediately than the frequency tables. Statistical significance. Even when we find patterns in data, often there is still uncertainty in various aspects of the data. For example, there may be potential for measurement errors. Even your own body temperature can fluctuate by almost 1 degree Fahrenheit over the course of the day. Or we may only have a snapshot of observations from a more long-term process, or only a small subset of individuals from the population of interest. In such cases, how can we determine whether patterns we see in our small set of data is convincing evidence of a systematic phenomenon in a larger process or population? Example number 2. In a study reported in November 2007 issue of Nature, researchers investigated whether pre-verbal infants take into account an individual's actions toward others in evaluating that individual as appealing or aversive. In one component of the study, 10-month-old infants were shown a climber character, a piece of wood with googly eyes glued to it, that could not make it up a hill in 2 tries. The infants were shown 2 scenarios for the climber's next try. One where the climber was pushed to the top of the hill by another character, a helper, and one where the climber was pushed back down the hill by another character, a hinderer. The infant was alternately shown these 2 scenarios several times. Then the infant was presented with 2 pieces of wood representing the helper and the hinderer characters, and asked to pick one to play with. The researchers found that of the 16 infants who made a clear choice, 14 chose to play with the helper toy. Oh, that's nice. One possible explanation for this clear majority result is that the helping behavior of the one toy increases the infant's likelihood of choosing that toy. But are there other possible explanations? What about the color of the toy? Well, prior to collecting the data, the researchers arranged so that each color and shape, red square and blue circle, would be seen by the same number of infants. Or maybe the infants had right-handed tendencies and so picked whichever toy was closer to their right hand. Well, prior to collecting the data, the researchers arranged it so half the infants saw the helper toy on the right and half on the left. Or maybe the shapes of these wooden characters, square, triangle, circle, had an effect. Perhaps, but again, the researchers controlled for this by rotating which shape was the helper toy, the hinderer toy, and the climber. When designing experiments, it is important to control for as many variables as might affect the responses as possible. It is beginning to appear that the researchers accounted for all other plausible explanations, but there is one more important consideration that cannot be controlled. If we did the study again with these 16 infants, they may not make the same choices. In other words, there is some randomness inherent in their selection process. Maybe each infant had no genuine preference at all, and it was simply random luck that led to 14 infants picking the helper toy. Although this random component cannot be controlled, we can apply a probability model to investigate the pattern of results that would occur in the long run. If the infants were likely to pick between the two toys, then each infant had a 50% chance of picking the helper toy. It's like each infant tossed a coin, and if it landed heads, the infant picked up the helper toy. So if we toss the coin 16 times, could it land heads 14 times? Sure, it's possible, but it turns out to be very unlikely. Getting 14 or more heads in 16 tosses is about as likely as tossing a coin and getting 9 heads in a row. This probability is referred to as p-value. The p-value tells you how often a random process would give a result at least as extreme as what was found in the actual study, assuming there was nothing other than random chance at play. So, if we assume that each infant was choosing equally, then the probability that 14 or more out of 16 infants would choose the helper toy is found to be 0.0021. We have only two logical possibilities. Either the infants have a genuine preference for the helper toy, or the infants have no preference, 50-50, and the outcome that would occur only 2 times in 1,000 iterations happened in this study. Because this p-value of 0.0021 is quite small, we conclude that the study provides very strong evidence that these infants have a genuine preference for the helper toy. We often compare the p-value to some cutoff value called the level of significance, typically around 0.05. If the p-value is smaller than that cutoff value, then we reject the hypotheses that only random chance was at play here. In this case, researchers would conclude that significantly more than half the infants in the study chose the helper toy, giving strong evidence of genuine preference for the toy with the helping behavior. Generalizability. One limitation to the previous study is that the conclusion only applies to the 16 infants in the study. We don't know much about how those 16 infants were selected. Suppose we want to select a subset of individuals, a sample, from a much larger group of individuals, the population, in such a way that conclusions from the sample can be generalized to the larger population. This is the question faced by pollsters every day. Example 3. The General Social Survey is a survey on societal trends conducted every other year in the United States. Based on a sample of about 2,000 adult Americans, researchers make claims about what percentage of U.S. population consider themselves to be liberal, what percentage considers themselves happy, and what percentage feel rushed in their daily lives and many other issues. The key to making these claims about the larger population of all American adults lies in how the sample is selected. The goal is to select a sample that is representative of the population, and a common way to achieve this goal is to select a random sample that gives every member of the population an equal chance of being selected for the sample. In its simplest forms, random sampling involves numbering every member of the population and then using a computer to randomly select the subset to be surveyed. Most polls don't operate exactly like this, but they do use probability-based sampling methods to select individuals from nationally representative panels. In 2004, the GSS reported that 817 of 977 respondents, or 83.6%, indicated that they always or sometimes feel rushed. This is a clear majority, but we again need to consider variation due to random sampling. Fortunately, we can use the same probability model we did in the previous example to investigate the probable size of this error. No, we can use the coin tossing model when the actual population size is much, much larger than the sample size, as then we can still consider the probability to be the same for every individual in the sample. This probability model predicts that the sample result will be within 3 percentage points of the population value, roughly 1 over the square root of the sample size, the margin of error. The statistician would conclude with 95% confidence that between 80.6% and 86.6% of all adult Americans in 2004 would have responded that they sometimes or always feel rushed. The key to the margin of error is that when we use a probability sampling method, we can make claims about how often, in the long run, with repeated random sampling, the sample result would fall within a certain distance from the unknown population value by chance, meaning by random sampling variation alone. Conversely, non-random samples are often subject to bias, meaning the sampling method systematically overrepresents some segments of the population and underrepresents others. We also still need to consider other sources of bias, such as individuals not responding honestly. These sources of error are not measured by the margin of error. Cause and effect conclusions. In many research studies, the primary question of interest concerns differences between groups. Then the question becomes, how were the groups formed? For example, selecting people who already drink coffee versus those who don't. In some studies, the researchers actively form the groups themselves. But then we have a similar question. Could any differences we observe in the groups be an artifact of the group formation process? Or maybe the difference we observe in the groups is so large that we can discount a fluke in the group formation process as a reasonable explanation for what we find. Example number 4. A psychology study investigated whether people tend to display more creativity when they are thinking about intrinsic or extrinsic motivations. The subjects were 47 people with extensive experience with creative writing. Subjects began by answering survey questions about either intrinsic motivations for writing, such as pleasure of self-expression, or extrinsic motivations, such as public recognition. Then all subjects were instructed to write a haiku, and those poems were evaluated for creativity by a panel of judges. The researchers conjectured beforehand that subjects who were thinking about intrinsic motivations would display more creativity than subjects who were thinking about extrinsic motivations. The creativity scores from the 47 subjects in this study are displayed in Figure 2, where higher scores indicate more creativity. Creativity scores, yeah, that's kind of cool. In this example, the key question is whether the type of motivation affects creativity scores. In particular, do subjects who were asked about intrinsic motivation tend to have a higher creativity score than subjects who were asked about extrinsic motivation? The Figure 2 reveals that both motivation groups saw considerable variability in creativity scores, and these scores have considerable overlap between the groups. In other words, it's certainly not always the case that those with extrinsic motivations have higher creativity than those with intrinsic motivation, but there may still be a statistical tendency in this direction. The mean creativity score is 19.88 for the intrinsic group compared to 15.74 for the extrinsic group, which supports the researchers' conjecture. Yet comparing only the means of the two groups fails to consider the variability of creativity scores in the group. We can measure variability with statistics using, for instance, standard deviation, 5.25 for the extrinsic group and 4.40 for the intrinsic group. The standard deviation tells us that most of the creativity scores are within about 5 points of the mean score in each group. We see that the mean score for the intrinsic group lies within 1 standard deviation of the mean score for extrinsic group. So although there's a tendency for the creativity scores to be higher in the intrinsic group on average, the difference is not extremely large. We want again to consider possible explanations for this difference. The study only involved individuals with extensive creating writing experience. Although this limits the population to which we can generalize, it does not explain why the mean creativity score was a bit larger for the intrinsic group than for the extrinsic group. Maybe women tend to receive higher creativity scores? Here is where we need to focus on how the individuals were assigned to the motivation groups. If only women were in the intrinsic motivation group and only men in the extrinsic group, then this would present a problem because we wouldn't know if the intrinsic group did better because of the different type of motivation or because they were women. However, the researchers guarded against such a problem by randomly assigning the individuals to the motivation groups. Like flipping a coin, each individual was just as likely to be assigned to either type of motivation. Why is this helpful? Because this random assignment tends to balance out all the variables related to creativity we can think of, and even those we don't think of in advance, between the two groups. So we should have a similar male-female split between the two groups. We should have a similar age distribution between the two groups. We should have a similar distribution of educational background between the two groups, and so on. Random assignment should produce groups that are similar as possible except for the type of motivation, which presumably eliminates all those other variables as possible explanations for the observed tendency for higher scores in the intrinsic group. But does this always work? No. So by luck of the draw, the groups may be a little different prior to answering the motivation survey. So then the question is it possible that an unlucky random assignment is responsible for the observed difference in creativity scores between groups? In other words, suppose each individual's poem was going to get the same creativity score no matter which group they were assigned to, that the type of motivation in no way impacted the score. Then how often would the random assignment process alone lead to a difference in mean creativity scores as large or larger than 19.88 minus 15.74, which equals 4.14 points? We again want to apply to a probability model to approximate a p-value, but this time the module will be a bit different. Think of writing everyone's creativity scores on an index card, shuffling up the index cards, and then dealing out 23 to the extrinsic motivation group and 24 to the intrinsic motivation group, and finding the difference in the group means. We, better yet the computer, can repeat this process over and over to see how often when the scores don't change. Random assignment leads to a difference in the means at least as large as 4.14. And they show a figure here that shows the results from 1,000 such hypothetical random assignments for these scores. Only 2 of the 1,000 simulated random assignments produced a difference in the group means of 4.14 or larger. In other words, the approximate p-value is 2 out of 1,000, which equals 0.002. This small p-value indicates that it would be very surprising for the random assignment process alone to produce such a large difference in group means. Therefore, as with example 2, we have strong evidence that focuses on intrinsic motivation tends to increase creativity scores as compared to thinking about extrinsic motivations. Notice that the previous statement implies a cause and effect relationship between motivation and creativity scores. Is such a strong conclusion justified? Yes, because of the random assignment used in the study, that should have balanced out any other variables between the two groups. So now that the small p-value convinces us that the higher mean in the intrinsic group wasn't just a coincidence, the only reasonable explanation left is the difference in the type of motivation. Can we generalize this conclusion to everyone? Not necessarily. We would cautiously generalize this conclusion to individuals with extensive experience in creative writing, similar to the individuals in this study, but we would still want to know more about how these individuals were selected to participate. The importance of diversity in psychological science. It is critically important that we carefully consider the extent to which our samples are truly diverse and random. the possibilities for alternative explanations for our results, and the degree to which our findings may or may not be generalizable. For example, historically, psychological science, and in science more broadly, has commonly used dichotomous categories of men and women to compare and contrast patterns of results. It is not always clear the degree to which these dichotomous terms have assessed sex, gender, or both. Further, this dichotomy of men and women, male and female, etc., fails to include many people who may not identify in a binary manner. Thus, it could be that there are limitations with interpretations of some of these findings. The topic of sex and gender can be considered as a lens for research, but also as its own major topic area in psychology. For this reason, we will cover the topic of sex and gender in detail in our unit related to self and identity. We want to highlight this topic for your consideration here. And there's also a link if you want to go to the chapter now. Just as considering diversity related to sex and gender is important, so is considering diversity more broadly. For example, factors including, but not limited to, race, age, geographic location, socioeconomic status, and more can have important influences on many research questions. We will highlight the need for diversity and inclusion in psychological science throughout our course and encourage you to continually question the degree to which our science can be more inclusive and diverse. In conclusion, statistical thinking involves the careful design of a study to collect meaningful data to answer a focused research question, detailed analysis of patterns in data, and drawing conclusions that go beyond the observed data. Random sampling is paramount to generalizing results from our sample to a larger population, and random assignment is key to drawing cause and effect conclusions. With both kinds of randomness, probability models help us assess how much random variation we can expect in our results in order to determine whether our results could happen by chance alone and to estimate the margin of error. So where does this leave us with regard to the coffee study mentioned at the beginning of the module? We can answer many of the questions. This was a 14-year study conducted by researchers at the National Cancer Institute. The results were published in the June issue of the New England Journal of Medicine, a respected peer-reviewed journal. The study reviewed coffee habits of more than 402,000 people ages 50 to 71 from 6 states and 2 metropolitan areas. Those with cancer, heart disease, and stroke were excluded at the start of the study. Coffee consumption was assessed once at the start of the study. About 52,000 people died during the course of the study. People who drank between 2 and 5 cups of coffee daily showed a lower risk as well, but the amount of reduction increased for those drinking 6 or more cups. The sample sizes were fairly large, and so the p-values are quite small, even though percent reduction in risk was not extremely large, dropping from 12% chance to about 10 to 11%. Whether coffee was caffeinated or decaffeinated did not appear to affect the results. This was an observational study, so no cause and effect conclusions can be drawn between coffee drinking and increased longevity, contrary to the impression conveyed by many news headlines about this study. In particular, it's possible that those with chronic disease don't tend to drink coffee. This study needs to be reviewed in the larger context of similar studies and consistency of results across studies, with the constant caution that this was not a randomized experiment. Whereas a statistical analysis can still adjust for other potential confounding variables, we are not yet convinced that researchers have identified them all or completely isolated why this decrease in death risk is evident. Researchers can now take the findings of this study and develop more focused studies that address new questions. Wow, that was a lot to take in. So I think I'm going to listen to this chapter a few times and maybe come up with a few ideas of my own. I'll go over the terminology in the next episode. By the way, terminology is only available on the YouTube channel. Not too many people who listen to podcasts want me to talk about definitions. So it's a separate playlist. I'll see you soon. Make sure you hit that subscribe button. You don't want to miss the next chapter.